Today we will be looking at exponential models, specifically graphing and modeling. An exponential function is a function whose, with general form, y equals a times b to the x power, where a is not equal to 0 and b is larger than 0. B is also not equal to 1. The b base is what is known as a constant. Note our most basic function, y equals 2 to the x power. We're just going to insert the x value we're evaluating in for the exponent. Remember, if you have a negative exponent, you have to flip your fraction down. So 2 to the negative 2 is actually 1 over 4. 2 to the negative 1 is 1 over 2 to the first, or 1/2. The next one is 1, then 2, then 4, then 8. So now we are actually ready to graph. Okay, so we're going to graph -2, -1/4. We have -1, +1/2, 0, 1, 1, 2, 2, 4, and 3, 8. Okay, so now other things that are important to keep in mind. Our domain here is all real numbers, so -infinity to infinity. And our range is actually 0 to infinity. And that 0 has a parenthesis because we actually have a horizontal asymptote at the x-axis. And remember, it's like a pretend line that the graph approaches but doesn't cross. Okay, so our asymptote is the line y equals 0. And then our y-intercept is at 0, 1. In our next example, we're going to graph y equals 2 times 3 to the x power. Notice that our xy table, we have for the x value of -2, we have 2 over 9. For the x value of -1, we have 2 over 3. For the x value of 0, we have 2. 1, we have 6, and 2, we have 18. Now we are ready to go over and graph. So 2 divided by 9 is approximately 0.2 repeating. So when we graph it, it will be very close to the y-axis. 2/3 is approximately 0.6 repeating. Okay. Let's see. 0, 2. And let's see, 1, 6. And I'm not going to waste my time and effort to graph 2, 18. Okay, so note to self, our domain again is all real numbers. Our range is from 0 to infinity. And our asymptote is the line y equals 0. Right? Our asymptote is located here. Our y-intercept is the point 0, 2. Now take a minute and try this on your own. This is what your graph should look like. Note that we have a y-intercept of 0, 1. Our domain is -infinity to infinity with parentheses. Our range is parentheses 0 to infinity, another parenthesis. And our asymptote is the x-axis, y equals 0. If we look at the next type of problem, we're going to graph y equals 1 over 3 to the x power. Same kind of thinking. We're going to start off with an xy table. And we're going to use the same x values we've used today so far. If we take 1/3 to the -2 power, remember it's like saying 3 squared, which would be 9. If we take 1/3 to the negative 1, it would be 3 to the first, which would be 3. 1/3 to the 0 power would just be 1. 1/3 to the first would be 1/3, and 1/3 squared would be 1/9. So -2, +9 when we go to graph. -1, +3. 0, 1. 1 and 1/3. And then 2 and 1/9. Okay, note to self, our domain again is all real numbers. Our range is 0 to infinity. Our asymptote this time is still the y-axis. And our y-intercept is 0, 1. Take a minute and try the next one. And hopefully you get something that looks something like this. So for exponential growth, as the value of x increases, the value of y also increases. And our exponential growth is this black curve here. If we have exponential decay, as the value of x increases, the value of y decreases. So this would be our exponential decay growth or decay model. And then the asymptote is a line that the graph approaches but does not cross. So our asymptote in this case is the x-axis again. Okay. So for exponential functions, for the function y equals a times b to the x power, if b is larger than 1, the function is exponential growth. If a is larger than 0 and b is between 0 and 1, the function represents exponential decay. In either case, the y-intercept is 0, a, and the domain is all real numbers. The asymptote is y equals 0, and the range is 0 to infinity. So in our next type of problem, we're going to identify it as growth or decay, and then find the y-intercept. So the trick with a, I look at this 0.7, and I have to determine, is it larger than 1, or is it between 0 and 1? Well, 0.7 is between 0 and 1, so therefore this is decay. And remember to find the y-intercept. All we have to do is plug 0 in for x. And in this case, we do get 1. So our intercept is located at 0, 1. Okay, so in letter B, whatever it is you're taking to the x power, is that larger than 1 or between 0 and 1? Well, 2 is larger than 1, so therefore B is growth. And remember to find the y-intercept, we will put 0 in for x. And note to self, we do get 0.25. So therefore, y-intercept is 0 and 1/4. For modeling, our growth factor. For exponential growth, the b is the growth value. For exponential decay, we call b the decay factor. And this is the general formula that we'll use for modeling. Okay. Where a is the amount after t time periods, little a is the initial amount or starting amount, r is the growth or decay rate, it is expressed as a decimal, and t is the number of time periods. So in our next example, you buy a savings bond for $25 that pays a yearly interest rate of 4.2%. What will the savings bond be worth after 15 years? The first thing you have to determine is if this problem is growth or decay. If it's paying an interest rate, that means the account is growing or the bond is growing. So we're going to call this growth. Step 2 is to define our variables. So we do not know the ending amount. So I'm going to leave that as a question mark. Our initial amount or starting amount is 25. Our rate as a decimal, remember for percentages for rate, you have to move the decimal point 2 places left. So 0.042. And if I want to know what is worth after 15 years, my time is 15. In step 3, all we're going to do is we're going to plug into our formula. A equals little a, parentheses 1 plus r to the t power. Okay, so it looks to us that we're going to have a equals 25, parentheses 1 plus 0.042 to the 15th power. And then I just type that into a calculator exactly like I see. Hopefully you find a bond value of $46.34. If we look at our next example, the initial value of a car is $30,000. Okay, initial value. After 1 year, the value of the car, 1 year, the value is $20,000. Estimate the value of the car after 5 years. So this problem is slightly different. What we will do first is decide if it is growth or decay. So did our initial value go up or did it go down? Well, hopefully you've recognized it went down. So we know this is a decay problem. Now this problem is unique because we have to set it up, we have to figure out what the rate of decline is. So we know our ending amount after 1 year is $20,000. We know by the first statement that the initial amount is $30,000. We don't know the rate, and we do know the time as 1. So when we set up our formula, we will have our 20,000 equals 30,000 times 1 plus r to the first power. Well, how are we going to solve for r? Well, hopefully you recognize that this is multiplication, so we're going to divide. And we do get 2/3 equals 1 plus r. 1 plus r to the first is just 1 plus r. Now, to find r, we have to subtract 1, and 2/3 minus 1 is negative 1/3. Now we have all the information to find the value of the car after 5 years. So we have big A equals our initial amount, which would be 30,000 times 1 minus 1/3 to the 5th. And then I would type it into a calculator exactly like you see. And hopefully you find a total of $3,950.62. Dun, 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 dun. Now you're ready to try some practice. Make sure you find the exponential growth and decay worksheet on Schoology.